Okay, then another example here is the volume of 1 kilogram of helium in a piston cylinder device is initially 5 meter cube. Now helium is compressed to 2 meter cube while its pressure is maintained constant at 130 kilopascal. Determine the initial and final temperatures of helium as well as the work required to compress it. Okay, so we can make the assumption that helium is an ideal gas. Why? Because if we look at table A1 and read the critical pressure of helium, it's gonna be 0.23 megapascal, which is higher than the pressure we have, which is 0.12 megapascal. Basically, we are away from the critical point. We are working at lower pressures. And this can help us to assume the helium as an ideal gas. So that means that we can use ideal gas equations, ideal gas equation of state, to be able to figure out the properties of helium. Okay, then once we make this assumption that helium is an ideal gas, now the volume of 1 kilogram means they are giving us the mass 1 kilogram, and then they are giving us the volume as 5 meter cube. It is compressed means there is a boundary work being done, and it is being compressed to 2 meter cube. The volume is getting smaller, but throughout the process the pressure is constant. Now, to figure out the initial and final temperatures of this gas and the boundary work, probably figure out the temperatures, we can use the ideal gas equation, right? And if you remember, you can write ideal gas equation for the first and the second state of the same system. So we can say P1V1 is equal to MRT1. And we can also say P2V2 is equal to MRT2. Well, here it's a closed system, so MR terms will stay the same. And if you solve both equations for MR, that means they are equal to each other. So basically, P1V1 over T1 is equal to P2V2 over T2. Right? And besides that, we are also given the pressure is gonna be the same. So actually P1 is equal to P2. So you can cancel these out. So what happened is V1 over T1 is equal to V2 over T2. Since V1 and V2 is given, and can we calculate what T1 and T2 is? Okay, so first of all, how we can figure out one of the temperatures? Maybe we can use one of the ideal gas equation to figure it out. For example, let's take a look at the first state. We know the pressure, we know the volume, we know the mass, and R is given. Yes, so from that equation, you can figure out what T1 is. Okay, let's do that. So basically, T1 is equal to P1V1 over MR, 130 kilopascal, 5 meter cube. M is 1 kilogram. R is given 2.0769 kilopascal times meter cube per kilogram Kelvin. Okay, so let's look at the units are matching well. Okay, we end up with calculating the temperature in kelvins, and T1 is equal to 312.97 Kelvin. We figured out T1. We can plug this in here to figure out what T2 is. Okay. You could have also used just the ideal gas equation here because you know the pressure, right? And you know V2 MR. You can also calculate T2 from that equation. That's also possible. Or you can just use this relationship to solve it for T2. Okay, let's do that. T1 is this, and then V2 is 2 meter cube over V1 is 5. Then the second temperature is 125.19 Kelvin. Okay, we were able to figure out both first and second state temperature for this gas. All right, so the next thing they're asking is the boundary work, and we know the equation for the boundary work, right? We know that it is from state 1 to state 2, P dV. Okay, since pressure is constant, it gets out out of the integral, and it's going to be P times delta V. In other words, P times V2 minus V1. Okay, and then the pressure is 130 and V2 is 2, V1 is 5, and it's gonna be minus 390 kilojoule. Okay, so that's the boundary work. Negative means compression, remember.